Hello, students, and my dear viewers, and all my viewers who are listening to my video, who are following me, all the followers who are following me on YouTube. So I hope you are all good, all well, and I am again here with something new, something more interesting and exciting. And of course, it's the continuity of one of my previous lectures, that is viscosity. I'm Professor Dr. Moina Akhtar Mughal from Dr. Mchem Institute of Chemistry, University of St. John, Shiro. And I'm here with something new, something interesting, something more exciting, and something, of course, you will be interested in because previously I've been discussing with you the viscosity in quite a detail, and I explained you how to what is viscosity first of all, what are its different parameters to calculate different types of viscosity, and then of course I told you what were all those parameters, starting from relative viscosity, of course the different parameters. There are relative viscosity, specific viscosity, then reduced viscosity, then intrinsic viscosity, inherent viscosity, and absolute viscosity. So today I thought that I should share with you one of my my own synthesized monomers, which I have synthesized during my research journey, and I was successful in getting amazing results of that monomer. So today I thought that I should make you learn how to calculate reduced viscosity of a monomer, right? So what is, first of all, reduced viscosity? Reduced viscosity is simply it's a ratio between the specific viscosity and corresponding concentration. It is simply calculated by what is viscosity is can be represented by, of course, eta. So it's simply calculated by the formula eta reduced equals to specific viscosity over concentration. When you divide specific viscosity with concentration, you are going to get reduced viscosity, and you are going to plot a graph between reduced viscosity and concentration, right? So this is how you're going to go along with this reduced viscosity method. So let's start the slide share. Okay, so this is it. There we are. It's reduced viscosity. Now, how to calculate reduced viscosity for monomer? As I just mentioned, that I'm going to explain you reduced viscosity of one of my monomers, which I have prepared during my research journey. It was an amazing experience, right? And I was successful. I was very happy as I achieved this these results with a lot of, hard work, with a lot of struggle. So there we are. What is reduced viscosity? It is the ratio between specific viscosity, which I just have mentioned. It has a specific and corresponding concentration. Reduced viscosity can be calculated by this formula, that is reduced viscosity here equals to reduced viscosity, that is specific viscosity over concentration. If you divide these two things, you are going to get the value for reduced viscosity. Okay. So here we are. Okay, so now this was the monomer of whom I was talking about, that I've calculated the reduced viscosity. It's simply 6,6-methylene bis 1-naphthaldehyde. You can see a methylene group, a bridging group between these two naphthaldehyde rings, right? And this was the monomer whom reduced viscosity today we are going to calculate. And you can see that this methylene group is at the 6,6 position of these both naphthalene rings, naphthaldehyde rings, right? So and we can also call it dialdehyde. So this viscosity of dialdehyde was measured by calibrated viscometer. Yes, of course, calibrated viscometer was used. As I have mentioned before, that we used calibrated viscometers. And I have explained how we are going to calibrate viscometer, the Osborne viscometer. So the Osborne viscometer was used for this measurement. Okay, now definitely when we are measuring the viscosity, we need a solvent. So now DMF, that is dimethyl formamide, was used during this whole viscometric studies, as this was chosen as the most effective solvent for this monomer MBN. Now I have abbreviated monomer, that is 6,6-methylene best 1-naphthaldehyde, with this MBN abbreviation, right? So as this monomer was not easy to dissolve in any other organic solvent, so this was DMF was selected as the chosen as the best solvent to get this MBN diluted, right? So it was first of all recrystallized in it, and even this was even pretty hard. It was difficult to recover back the precipitates. Once it was dissolved, it took a lot of time in getting it dissolved, and then recovering back the precipitates was another goal. So that was quite a different, difficult path. Okay, after recrystallization and due to the pure solubility of this dialdehyde, it prohibits its further processing, or further its, okay, it's further processing. So the flow time of the DMF was noted at the temperatures, as I've mentioned in my previous lectures, that the Gallon-Kemp viscometric bath was used during the whole study, right? And there we have set down the temperatures starting from 283 degree Kelvin, 293 degree, 303, 313, and 323 degree Kelvin. This was the, temperatures were chosen to note down, the flow time of this DMF, right? And 10 degree Kelvin interval was maintained. Yes, of course, a 10 degree Kelvin interval was maintained at different low concentration solutions of ambient. The monomer were prepared by adding DMF to the pre-weighed ambient. Now, as I have mentioned earlier, that this monomer ambient was very, difficult. It was a difficult compound to dissolve, to get it diluted, to dissolve in any of the organic solvents, common solvents. So I have chosen DMF, and these were the very lowest concentrations were used just because of this its poor solubility in different in DMF even. So that was the reason of these, low concentrations which I have used here, and these were all in grams per deciliter. So the samples were prepared in the pre-weighed by taking the pre-weighed MDN, okay, that is methylene bisnaphthaldehyde. Okay, now definitely we need something to prepare our solvents in. So of course, a volumetric flask here, you can see a volumetric flasks were used to make these solutions of different, as we have to prepare different concentrated solutions, right? Solutions of different concentrations. So for making these solutions, flow, and of course flow time of different concentration solutions were recorded, having above mentioned concentrations, that is starting from 0.024, 0.034, 0.044, and so on. So at what was the temperature range? At about 283 degree Kelvin to 323 degree Kelvin. Now every time 15 ml solution was filled in the Oswald's viscometer, every time we have that U-shaped Oswald viscometer, and every time we used, I filled 15 ml of the solution into it, and then of course flow time was recorded as it started to flow from the upper mark, and it reached the meniscus, and we noted down that time, and that is called the flow time of that that solution, right? So the measurement at each temperature is made twice. So every measurement was an average of the three values were recorded, right? So at each temperature, that is, for example, as 283, three times we have to take the measurement, and do it again, and then at the next temperature, that is 293, again we took the three measurements, right? So thrice, every measurement was taken thrice, and average of the three values were recorded. Okay, average of the three were recorded as the flow time of the solution, right? Okay, the solvent DMF and the solution of ambient at different concentrations and temperatures helped in calculating relative viscosity, specific viscosity, eta inherent, that is inherent viscosity, reduced viscosity, intrinsic viscosity, and absolute viscosity. Yes, of course, these were all the viscosities that were then calculated, right? When we calculated the flow time of our solution, right, of our solution of ambient. The reduced viscosity is calculated. Now, how today's mission is to know and to calculate reduced viscosity. So the reduced viscosity is calculated by plotting a graph. As I have mentioned it earlier, that we are going to plot a graph between reduced viscosity and concentration. So let's see if I can find out that graph. Okay. The graph was plotted between reduced viscosity and concentration, and the reduced viscosity's unit was deciliter per gram, whereas concentration was on the horizontal side, and that one, the reduced viscosity was on the vertical side, right, on the y-axis, and this was on the concentration was on the x-axis. Here you can see a graph was plotted, right? So reduced viscosity can be calculated by dividing specific viscosity by concentration. Yes, we just mentioned the relationship between, you can see here a graph between reduced viscosity and concentration. Okay, the relationship between concentration and of ambient and is a straight line, right? We got a straight line. Right, when we plot a graph between reduced viscosity and concentration, we got a straight line, which satisfied Huggins' equation. Now, what is Huggins' equation? Huggins' equation is simply an equation that follows the equation of a straight line. That is y is equal to mx plus c. Now, we can also write it y is equal to mx plus c. We can write it like that: y is equal to c plus mx. Now, what is y? That is eta reduced. That is here. This is the y-axis, right? C is the intercept, which we can get from the intrinsic viscosity, right? Intercept can be calculated from intrinsic viscosity. And of course, m is the slope. This is the slope, that is kh. Eta square is the slope. And c is, of course, the x-axis. That is the concentration here. So this is, it simply satisfies the straight line. It satisfied this Huggins equation. Now, I explain each and every parameter of this, that is intrinsic viscosity, and that can be calculated easily, and this of course the slope, and of course the x-axis, and this follows the equation of a straight line. Okay, so Huggins equation is eta reduced equals to eta plus kh eta square c. This is equation A. Now, as I've just mentioned, this is y. Y is eta reduced, whereas this eta is c. That is your intercept, right? And this m is your slope. Mkh eta squares is your slope, and c is your concentration, which is on the x-axis. So this is a graph between y and x-axis. Y-axis, I've written also here. So now eta equals to c equals to intercept, that is this one, and m is the kh eta square, which is this one. This is the slope, and c is x-axis, of course. Okay, now Huggins constant. What is Huggins constant? We will discuss in my next lecture what is Huggins constant, but what is Huggins rule? What is Huggins constant? But whereas Huggins was the name of a scientist. Okay, it's enough for now. Huggins constant can be found from this equation, from this formula, that is kh. Okay, Huggins constant equals to slope over eta square. If you divide slope by eta square, you are going to get the value for Huggins constant. Whereas, how you are going to calculate slope? You will calculate slope equals to kh eta square. If you rearrange this equation, you will get slope equals to kh eta square. Okay, so the reduced viscosity was plotted against concentration according to Huggins equation A, that is this one, right? And the intrinsic viscosity calculated from the intercept. Okay, the intrinsic viscosity, that is this one, was calculated from the intercept. Right now, what is the intercept? Actually, it's like just like that when you plot a graph between the two axes, that is a y and x axis, and you got a straight line. Now if that straight line, the point at which it cuts the y axis, right, and there's an x axis and there's a y axis, the point at which the straight line cuts the y axis is called the intercept, right? And from that value, we can calculate the intrinsic viscosity. That is the intrinsic viscosity. Actually, the point at which it cuts the y-axis. It's called the intercept. Okay, Hagen constant was obtained from the slope, whereas Hagen constant was obtained from the slope of that line. Okay, now, so as I've just mentioned, that if we plot a graph between reduced viscosity and concentration of ambient at these different temperatures and different concentrations, now here I've shown you the concentration started from 0.024 to 0.064 grams per deciliters at different temperatures. These are the different temperatures, that is 283, 293, 303, 303, and 323. And this is the reduced viscosity, the values of reduced viscosity in deciliter per gram. Now here in the graph, if we look at closely at the graph, we can simply see that reduced viscosity increases with the increase in concentration, right? And whereas it decreases with the increase in the temperature. If you increase the temperature, you will see a decrease, whereas if you simply see that it increases with the increase in the concentration. If you increase the concentration, you will see the increase in reduced viscosity, right? The values of reduced viscosity will increase. Now, what could be those reasons? Now, this is due to the following, of course, reasons. That is, as the concentration of the solution is increased above zero, the intermolecular forces come into play. The intermolecular forces they come into play, and these attractive forces between the molecules, they increases with the increase in the concentration. As you raise the concentration, these intermolecular forces, these attractive forces between the molecules, they will also increase with the increasing concentration. So the result, what would be the result of this? The result will be the increase in the viscosity, right? But when the temperature is raised, what will happen? When you raise the temperature, that is starting from 283, it will go to 293, 303, 313, and 323 degree Kelvin. The frequency of the vibration of the molecules increases, which prevail over, you can simply say, some of the attractive intermolecular forces. Hence, the internal resistance to the flow decreases, and molecules become more mobile, and we observe a decrease in the viscosity. Now, as simply it is been seen that at raised temperatures, that is here around here at raised temperatures, the free volume of the solution increases. The volume that is there, the free volume always, increases, facilitating jumping of the molecules. The molecules will jump more, right, as they will find more volume. Jumping of the molecule will be facilitated, right? And our molecules, or the segments that are there, as the frequency of jump increases, of course viscosity decreases. It just is the opposite of it. As the frequency of these jumping increases, of course the viscosity decreases. So that was about viscosity today, and I hope that you find this video interesting, and you find this slideshare interesting, and you have seen how we have plotted a graph between reduced viscosity and concentration, and we have seen the results that we found there, right? That with the increase in the temperature, what happens, right? And how it increases. Okay, so I hope you find this video interesting, and you will share among with your friends. You will learn it, and you will watch it more with more interest. And now you have learned one more aspect, that is how you are going to calculate the reduced viscosity of your monomer. Okay, so thank you very much. Hope to see you again with something new, something more interesting. Goodbye.